In the first set of problems, you are to find f plus g, f minus g, and fg and state the domain of each. Anytime you are creating functions from combining functions, whether algebraically or using compositions, you should compute the domain or determine the domain of each of the individual functions before you start, and then consider those domains as you arrive at the domains of your new functions. So the first function we have, f of x, is x minus 1 squared, which is a parabola, which has the equation as a polynomial, which would tell you that your domain is all real numbers. The second one is a line, which clearly has the domain all real numbers, because lines are defined everywhere and are arguably polynomials, if you want to think about them that way. Alright, so let's find f plus g first. So f plus g is equal to f, which is x minus 1 squared, plus 3 minus x. Well, we can't leave our answer that way because there's cleaning up we can do. So we expand x minus 1 and get x squared, and you don't need the parentheses, but I'm doing this for emphasis, minus 2x plus 1 plus 3 minus x. And then we combine like terms. X squared minus 3x plus 4, and that is our f plus g. Well, remember that when we define a function based on this as the sum of two other functions, its domain is the intersection of the domains of each of them, and anytime they're both all real numbers, the domain of the sum will also be all real numbers. So then we have f minus g, which is going to look very much the same. So f minus g equals x minus 1 squared plus 3, rewind, we're minusing, minus, and when you subtract, you need to make sure that you put whatever you're subtracting in parentheses because each term has to get subtracted. So then that gives us x squared minus 2x plus 1 from expanding our binomial minus 3 plus x. And then when we combine like terms, we get x squared minus x, because we have a minus 2x and a plus x at the end, plus 1 minus 3 would be minus 2. So that is the difference of these two functions. And again, the domain of this one will also be our real numbers, because when you do this combination, at least the three that we're doing here, the only time you have restrictions is if we have a quotient, and we'll do some of those in a minute. So now we want to go and find our f times g, which would be the third requirement here. So fg is equal to x minus 1 squared, let's try that, parentheses look kind of bad, times 3 minus x. So again, we expand the binomial first, and we get x squared minus 2x plus 1 times 3 minus x. Well, then to multiply this binomial into the trinomial, you're just going to multiply, let's multiply the x first. It doesn't matter which one you do first, but that way they'll be in proper order. So if I multiply negative x times x squared, I get negative x cubed. And then negative x times minus 2x would be plus 2x squared. And then negative x times 1 is minus x. And then I'm going to distribute the 3. Switching colors here to emphasize what's happening. So now I'm going to distribute the 3 to each of those. And watch how I'm going to do it. I'm going to do it, this is called vertical arrangement of your terms. So if I distribute 3 on there, I get 3x squared. So I'm going to line that up with my previous x squared term. See if you can actually tell that's a 2. That's better. And then 3 times minus 2x would be minus 6x. And then 3 times 1 would be 3. And then combining like terms gives us negative x cubed plus 5x squared minus 7x plus 3. And it should not surprise us that we multiplied a linear thing times a quadratic thing and wound up with a cubic thing. Because when you multiply things, their degrees add. And again, because both domains to start with were all real numbers, they'll be all real numbers still. So that's number 2. We're doing the same thing on number 4. The functions are a little uglier, but in a way this makes this problem easier, ironically enough. So let's watch and see how that happens. But first, remember you need your domains of each of the 2 functions you have, and the domain of the absolute value, because it's an absolute value, which if you think about what that graph looks like, it's a V, which means it exists to infinity in both directions, gives us all real numbers. The domain of this square root function is a little different because we are restricted to the fact that whatever's inside the square root, or any even root, must be greater than or equal to, let me fix that, greater than or equal to 0. And then if we subtract 5 from both sides, we get that x must be greater than or equal to -5, which in interval notation would give me -5 with a bracket to include the -5 because of the equal possibility, to infinity. And then remember, the domain of the 3 combinations we're working with in this first set is the intersection of the 2 domains. And in this case, and another way to think about that is the most restrictive of the 2, and the most restrictive of the 2 here, which is the intersection of the 2, is -5 to infinity. So let's go through and find these real quick. The reason this was going to be easier is that because of the uniqueness of the functions, we're not going to be able to do any cleaning up once we set them up, because f plus g is the square root of x plus 5 plus the absolute value of x plus 3, and that's all you can do. There's nothing you can do to simplify that. And so your domain is the most restrictive of the 2 we started with, so it is -5 to infinity. And then we go to f minus g, and literally the only difference in this one in terms of its notation is that one sign. So this is the square root of x plus 5 minus the absolute value of x plus 3. But again, the domain is the most restrictive of the 2, or the overlap of the 2, which is -5 to infinity. And then we have fg, which is probably the strangest looking result here, because you're going to do the absolute value of x plus 3 times the square root of x plus 5, and you write it just like that. That's all you do. And again, its domain, because it is the intersection of the domains of the 2 combining functions, is -5 to infinity with a bracket to show that it can be 5. I'm sorry, -5. On number 6, we're switching gears because now the directions told us to find the quotients of these 2, both possibilities, f over g and g over f. But again, we start by finding the domain of each of the functions we're working with. So f's domain is a square, because it's a square root, is going to come from the fact that whatever's inside my square root, or any even root, has to be greater than or equal to 0. So again, I isolate x, and I get that x has to be greater than or equal to 2, which would, in interval notation, be 2 to infinity. And the domain of g of x would come also from the square root, would be x plus 4 has to be greater than or equal to 0. Isolating x gives me x is greater than or equal to -4. And in interval notation, this one gives me -4 to infinity with a bracket to show that it can be -4. So now it would be smart, before we get bogged down in the details of what we're about to do, to remember that we want the most restrictive, and 2 to infinity is a smaller set than -4 to infinity. So this is the one that's going to be our starting domain for our 2 quotients. And you'll understand why I say starting in just a minute. So let's start with f over g. Pretty simple. You just write function f, which is the square root of x minus 2, over function g, which is the square root of x plus 4. And then you can actually go one step to simplify this by writing it all under one square root. which is just cleaner looking, but this is all you can do. That's our f over g function. But now our domain, which is starting as 2 to infinity. And I recommend that you always write your starting domain, even if you wind up modifying it. But then we have a restriction here that we didn't have in the two original functions because there's a denominator. So the denominator can't be 0, so we know that x is not allowed to be negative 4. But the reason that doesn't change our domain is that negative 4 is not in the interval 2 to infinity. So that is our domain. And this is our quotient. So now we go again to get the reciprocal as we were instructed to do. And that is g over f. So now the only difference is that we're going to have the x plus 4 on the top and the square root of x minus 2 on the bottom, which again we can simplify into one radical with x plus 4 over x minus 2 on the inside. And that's as simplified as we can get, but now we need our domain. And again, we start with our starting domain of 2 to infinity. But we have to make sure everything there works. Well, because we have a new restriction in that x minus 2 is in the denominator, so we know that x cannot be 2 because that would make the denominator 0. So we slash our starting domain and conclude that the actual domain here is from not including 2, so parenthesis 2 to infinity. And there's that one. Actually, we don't need a box around the whole thing, we just need it around the domain. Alright, number 8. Same set of directions, two new functions, same process. So again, we start with the domain of each, and x cubed is all real numbers, because there is no number you're not allowed to cube. And then I go to g of x, and I have a cubed root with a cube thing inside it. Well, the great news here is that if it's an odd root, x can be anything. I can take the cube root of negative 8 and I get negative 2. So there's no restriction on an odd root. So this too is all real numbers, which is a little bit surprising for most students. But it is. So then we want f over g. And we get x cubed over the cube root of 1 minus x cubed. And there's nothing I can do to simplify that, so that is my quotient. And since the domain is the overlap of the two, or at least it starts as the overlap of the two, I write all real numbers. And we have a new restriction because we have a denominator, and that is that what's in the denominator cannot be 0. And the only way what's in the denominator is 0 is if 1 minus x cubed is 0. So I'm going to write that as, well, that can't be 0. It can be anything else, it just can't be 0. So then I add x cubed to both sides, so what I get is that x cubed cannot be 1, and the only number you can cube and get 1 is 1, so x cannot be 1. So that is the only exclusion from the original starting domain of all real numbers. So our actual domain for this one is, I don't know why I did a parenthesis. Well, I do know why I did a parenthesis, because it's going to be negative infinity to 1, parenthesis union, parenthesis 1 to infinity. So basically anything but 1. And then we go to our other assigned new function, which is the reciprocal, the one we just found. So now we're going to have the cube root, let's try to get that a little better, the cube root, bear with me one second, I'm going to try one more time to make a 3, the cube root of 1 minus x cubed. My pen does not want to make a 3 all of a sudden. Okay, over x cubed. And nothing I can do to simplify that, so I'm going to leave it. And then I'm going to find my domain, which starts as all real numbers. But again, I have to look at the denominator, and in this case we have x cubed in the denominator, and we know that it cannot be 0, which means that x cannot be 0. So we exclude 0 from the domain of this one. So our domain is negative infinity to 0 union 0 to infinity. And we have completed number 8. One more for this video. We're going to take a look at number 10, which is a much simpler problem than most students seem to think it is upon first glance. But the directions are pretty clear in that you are to take this picture they gave you, and I've made a copy on your study guide so that you can mark all over it as we go. But we're to find, it says sketch the graph of f minus g by subtracting the y-coordinates directly from the graphs, and then graph the difference in your calculator to see how close you came. So we're going to do all that together here. So we begin over on the left side, and we were given that our window here is -5, as you can see there on your study guide, -5 to 5, -5 by 5, 5 to 5 by -10 to 25. So what that tells you is that we're counting by 5s on the y and by 1s on the x. So if I go to -5, which is my x, then for x squared, the y-coordinate up here would be 25. Let me see if I can switch colors. That bright green is not going to show up too good on the white background. So here we go. Try again. So this value is 25. And at -5, if you plug -5 into g, you would have 4 plus 15, which would be 19 at that same location, -5. So we do 25 minus 19, which gives us 6. So now we're going to go over to our graph, and we're going to go to the left 5 and up 6. But remember, we're counting by 5s on x, so we want to match their scale just so we'll have a proper frame of reference. So we're going to go to the left 5 and up 6 will put me about right there. Alright, so we plotted our first point. Alright, so now we go back and look at -4, and at -4 the functions cross because you get 16 for both of them. So I'm going to go 16 minus 16 would give us 0 to graph my difference, because remember what we're graphing here is f minus g of x. So then we go to -3, and we plug -3 into g, which is the red graph, and we get 4 plus 9, which would be 13. And then if we square -3, we get 9. But now these are upside down, so you have to do blue minus red, so it's 9 minus 13, which is -4. But we're counting by 5, so over here on our graph, you're going to go not quite to the first mark down when you go to the left 3. Then to the left 2, and obviously -2 squared is 4, and if I plug -2 into my g of x, I get 4 minus 3 times -2 would be 4 plus 6, or 10. So 4 minus 10 is -6, which would put me right here, roughly. And then I go to -1, and at -1 I get 1 from the parabola, and I get 4 minus 3 from the other one. I get, that's not right, what am I doing? 4 minus 3 times -1 would be 4 plus 3, which is 7, and then it's 1 minus 7, which is also -6. And we keep going, and then at 0, we have 0 for the parabola, and we have 4 for the line. So 0 minus 4 is -4, which I plot right there on the y-axis. And then at 1, I get 1 on the parabola, and I get 1 for the line, so they both cross at 1, so 1 minus 1 is 0. So I'm going to plot 0 at x equals 1. And then 2 is 2 squared gives me 4, and 4 minus 3 times 2 would be -2. So 4 minus -2 is +6. And then at 3, we get 9 for the parabola, and then 4 minus 9, which would be -5 for the line. So 9 minus -5 would be 14. So that would be about here. and then we plug in, did I say that right? 9 minus, yeah, okay, 14. All right, and then we're going to go to, no, now we're plugging in 4. I'm sorry, I lost my train of thought there for a second. All right, so 4 squared would give me 16 for the parabola, and then 4 minus 12 would be negative 8. So now we have 16 minus negative 8, which would be 24. So we're going to go to the right 4 and up. So we're counting by 5s. Remember, 5, 10, 15, 20, 25 would put me about right there. And then we go to the right 5, and we plug in 5, and we're going to get 25 from the parabola. And that would give us 4 minus 15, which would be negative 11. 25 minus negative 11 is 36. So that's 5, 10, 15, 20, 25, 30. 36 is going to be right in there. And then let's switch colors to draw the line for this graph. And it's just going to follow your dots. And it should not surprise us that we came out with a parabola. It's a pretty ugly parabola. Let me try it, see if I can't do better. It should not surprise us that we came out with a parabola because of the fact, and I bumped the wrong thing. Try it, bear with me 1 second. Because we, okay, I'm going to try this one more time, and then I'm just going to start crying. We added a parabola to a linear thing, so we should end up with a parabola because the x squared is not going to go away. We're just going to combine terms and get a parabola. And so this is what your picture looks like. And so now let's go to our picture from our calculators. And you can see that this one looks very much like what we just produced, which confirms what we did. And that's the end of this video.